Okay, it's getting colder again, so that's good. It's way better than having it be super hot and turning on the air conditioning all the time. So, I finally got my tablet working in a way where it's not really Bluetooth, but I actually had to install some drivers to make it work with USB cable connected. The thing is that my USB cable is kind of flaky. Doesn't really connect well because it's not really meant for the tablet. It was meant for my keyboard when I had a wired keyboard, uh, or like the wireless keyboard, those gaming keyboards, when I could still type on a normal one. Um, but yeah, it's should be good now. So really wanted to make sure I don't waste time trying to set that up, so I did that ahead of time. Um, we're gonna start something new, finally, and then anything else that we need to install, whatever, we can just do it as we go along. I think at this point, we have something at least minimal to get by. So I've already cloned my repo, and we're kind of back in action here. Um, I want to do this. I want to just get started reading this book here. It's hard, but it's called Linux Kernel Development, and it's basically, I'm going to read this. It's a thorough guide to the design and implementation of the Linux kernel. It's an older book. It's like written in 2000, I think 10 or close to it. But I think it's a. I've never read it before, but it's a good. It seems like a good start to learning how the Linux kernel works. Um, I think it discusses the 2.6 kernel, so it's older, but I think 2.6 kernel is pretty much the kernel that modern Linux kernels are kind of built on top of. Like prior to that, not really familiar with the history, but prior to that, there was like a different way of doing things in kernel development. But after 2.6, things have just been consistently like improved on the same type of code base, I guess. I don't know. Um, yeah, and then like version numbers are just arbitrary. So even though we're like kernel 6 point, I think 11 right now or something like that. It's just not. It's not that 6 is way more significant than 5, and 5 is more significant than 4, and so on. It's just arbitrary. I think Linus has said that he just increments a version whenever he feels like it gets too high. So yeah. Um, as far as the book goes, I think there is a PDF. Oh, here's my instructions. There's a PDF for this book. Let's download that so that we can just like kind of walk it through. Linux kernel development, uh, third edition PDF. So this one, I guess this one works. Docdevelopmentdurable.org. Is there one? Oh, there's one on GitHub too. So you can just find this at anywhere. I'm just gonna download it. I'm just gonna open it up too. So yeah, we'll do what we did. We'll do what we did with our head first C, and we'll just read and just go from there. I mean, uh, I'm basically like an audiobook. But we'll learn a lot of operating system stuff as we go along. And I've never really played with the Linux kernel to this level, so it'll be interesting to see. Um, yeah. Okay. So let's set ourselves up here. Blah blah blah. Okay. Should we just go chapter 1? Let's just go chapter 1. Yeah. So kernel version. So this is the preface. Okay. So let's do this. Let's read some of this stuff. Some of the preface stuff. Yeah. Okay. And let's kind of full screen. So I can now just go 1, 2, or 2, 1, 2, 1, 2. Okay. Should be easier now. Okay. So, using this book, developing code in the kernel does not require genius, magic, or a bushy Unix hacker beard. The kernel, although having some interesting rules of its own, is not much different from any other large software endeavor. You need to master many details as with any big project, but the differences are quantitative, not qualitative. It is imperative that you utilize the source, so we have to use the source code. The open availability of the source code for the Linux system is a rare gift that you must not take for granted. It is not sufficient only to read the source, however. You need to dig in and change some code. So that's what we're going to be doing. That's like our interactive part of it. Find a bug and fix it. Improve the drivers for your hardware. Add some new functionality, even if it is trivial. Find an itch and scratch it. Only when you write code will it all come together. All right, I'm motivated. Let's do it. Kernel version. This book is based on the 2.6 Linux kernel series. It does not cover older kernels except for historical relevance. We discuss, for example, how certain subsystems are implemented in the 2.4 Linux kernel series, as their simpler implementations are helpful teaching aids. Specifically, this book is up to date as of Linux kernel version 2.6.24. So that's what we're going to be looking at. Although the kernel is a moving target and no effort can hope to capture such a dynamic beast in a timeless manner, my intention is that this book is relevant for developers and users of both older and newer kernels. Although this book discusses the 2.6.34 kernel, I have made an effort to ensure the material is factually correct with respect to the 2.6.32 kernel as well. That latter version is sanctioned as the enterprise kernel by the various Linux distributions, ensuring we will continue to see it in production systems and under active development for many years. And 269, 2618, and 2627 were similar long-term releases. So just for your information, 2.6.32 is the kernel that Ubuntu 10 used, and that's the reason why we installed a virtual machine there, just in case if we need it. I think in the beginning we probably won't because we're just gonna be compiling, maybe. But if we do need it, we'll set it up correctly. Anyway, audience. So this book targets Linux developers and users who are interested in understanding the Linux kernel. It is not a line-by-line commentary of the kernel source, nor is it a guide to developing drivers or a reference on the kernel API. Instead, the goal of this book is to provide enough information on the design and implementation of the Linux kernel that a sufficiently accomplished programmer can begin developing code in the kernel. I think that's us. Kernel development can be fun and rewarding, and I want to introduce the reader to the world as readily as possible. Okay, yeah, so just I guess we had to also have some expectations here. Is that I think our C is okay. We just got off of head first C and we did some practice here and there. So we're going to have to also at the same time as we're learning the kernel, continue to learn our C. So yeah. Anyway. This book, however, in discussing both theory and application, should appeal to readers of both academic and practical persuasions. I have always been of the mind that one needs to understand the theory to understand the application, but I try to balance the two in this work. I hope that whatever your motivations for understanding the Linux kernel, this book explains the design and implementation sufficiently for your needs. Okay, cool. All right. So he goes, I assume that the reader knows a C programming language and is familiar with Linux systems. Some experience with operating system design and related computer science is beneficial, but I try to explain concepts as much as possible. If not, the bibliography includes some excellent books on operating system design. This book is appropriate for an undergraduate course introducing operating system design as the applied text, if accompanied by an introductory book on theory. Okay. Oh well. I mean, I guess we'll learn along. Okay. All right. Robert Love. Okay, by the way, yeah, please, if you can, just buy the book on Amazon or something. Yeah. Robert Love is an open source programmer, speaker, and author who has been using and contributing to Linux for more than 15 years. Robert is currently senior software engineer at Google. This was a long time ago, so I don't know where he is now. So, yeah, where he was a member of the team that developed the Android mobile platform's kernel. Awesome. So this person knows what he's talking about. He's pretty much the guy who helped make the Android kernel. Cool. And he's probably also contributed to the Linux kernel too, I bet. Let's see. Oh, Robert's kernel projects includes the preemptive kernel, the process scheduler, the kernel events layer, iNotify, VM enhancements, and several device drivers. Nice. Cool. And he lives in Boston. All right, let's get started. The introduction to the Linux kernel. This chapter introduces the Linux kernel and the Linux operating system, placing them in the historical context of Unix. Today, Unix is a family of operating systems implementing a similar application programming interface, or API, that built around shared design decisions. But Unix is also a specific operating system, first built more than 40 years ago. To understand Linux, we must discuss the first Unix system. Cool. The history of Unix. Okay, so after 4 decades of use, computer scientists continue to regard the Unix operating system as one of the most powerful and elegant systems in existence. Since the creation of Unix in 1969, the brainchild of Dennis Ritchie and Ken Thompson has become a creature of legends, a system whose design has withstood the test of time with few bruises to its name. Okay, exciting. Okay. Unix grew out of Multics, a failed multi-user operating system project in which Bell Laboratories was involved. With the Multics project terminated, okay, so history goes is that uh, Multics was canceled, and then spoiler alert, like Ken Thompson, I think his wife was taking a vacation with his like newborn baby or something, and then he decides to literally like go, okay, I'm gonna write an operating system in like a few weeks, and then and that project that he did on the side was literally Unix. So members of the Bell Laboratories Computer Sciences Research Center found themselves without a capable interactive operating system. In the summer of 1969, Bell Lab programmers sketched out a file system design that ultimately evolved into Unix. Testing its design, Thomson implemented the new system on an otherwise idle PDP-7. So at this point, the PDP-7 was like an older computer. So we look at PDP-7. So what year was this? 1970. Let's just say 1970. So at this point, it was 1970, and the PDP-7 was released in 1965. So it was already like a 5-year-old computer, and I think it was also like marketed to be like a budget one too. Yeah, it was cheap but powerful. Okay, so So at this point, they were developing on like on an older computer too. So it's not like they had a bunch of resources. Um, I think that's a pretty cool picture too. So this is a PDP. This is the PDP-7. I'm guessing here this is like their terminal here. So this is where they actually typed in stuff, and then I think it printed out the output here. So there's like no screen back then. It was like literally like the output would just come out in paper, I would assume. And then yeah, this stuff would be like like in here will probably be like the CPU and memory. Literally, it was that big. Like memory was not even like DRAM memory. It was just more like um what we call core memory, I'm guessing. So let's see. Let's see if it used core memory. Let's see. Core memory? Yeah, core memory. So it had how much? It had 4K words. So 9.2 kilobytes worth of RAM. And this is what it looked like. These little things. But then this is only 128 bytes. It looks like this inside. So this is the RAM. So there was like no like DRAM chips or whatever you call them nowadays. Okay, so in 1971, Unix was ported to the PDP-11, and in 1973, the operating system was rewritten in C, an unprecedented step at the time, but one that paved the way for future portability. The first Unix widely used outside of Bell Labs was Unix System 6 Edition, or more commonly known as B6. Other companies ported Unix to new machines. Accompanying these ports were enhancements that resulted in several variants of the operating system. In 1977, Bell Labs released a combination of these variants into a single system, Unix System 3. In 1982, AT&T released System 5. What about System 4? It was an internal development version. Okay. The simplicity of Unix's design, coupled with the fact that it was distributed with the source code, led to further development at external organizations. The most influential of these contributors was the University of California at Berkeley. Variants of Unix from Berkeley are known as the Berkeley Software Distributions, or BSD. Berkeley's first release, 1BSD, in 1977 was a collection of patches and additional software on top of Bell Labs' Unix. So, important to understand that BSD is like legit Unix. So there's like FreeBSD. So FreeBSD. This is like a derivative of I guess like some sort of distro, I guess, of BSD, and it's really close to Unix. Um, I mean, even more so than Linux, because Linux is just kind of like a clone. So they're like two different operating systems. Like if we take a look at FreeBSD and Linux, they are different. Even though they had like the same type of tools you would find like familiar, like Bash, um, uh, I don't know, NanoVim, whatever. Like these tools, underneath the hood, they are different operating systems. So yeah. 2BSD in 1978 continued this trend, adding CSH and VI utilities, which persist on Unix systems to this day. The first standalone Berkeley Unix was 3BSD in 1979. It added virtual memory to an already impressive list of features. A series of 4BSD releases, 4.0 BSD, 4.1 BSD, 4.2 BSD, 4.3 BSD, followed 3BSD. These versions of Unix added job control, demand paging, and TCP/IP. In 1994, the university released the final official Berkeley Unix, featuring a rewritten VM subsystem. So I think VM meaning virtual memory, um, or I guess in general, like process management thing, as 4.4 BSD. Today, thanks to BSD's permissive license, development of BSD continues with the Darwin, which is what Mac OS is based off of. FreeBSD, NetBSD, and OpenBSD systems. In the 1980s and 1990s, multiple workstation and server companies introduced their own commercial versions of Unix. These systems were based on either an AT&T or a Berkeley release and supported high-end features developed for their particular hardware architecture. Among these systems were Digital's True64, Hewlett-Packard's HPUX, IBM's AIX, Sequence Dynix, SGI's IRIX, Sun Solaris, which is now Oracle, and Sun OS. So I think HPUX, AIX, and Solaris are still like used today. Like they're still being developed today. So Unix is still out there. Like Unix has it in its Unixy form, other than BSD, I guess. Um, the original elegant design of the Unix system, along with the years of innovation and evolutionary improvement that followed, has resulted in a powerful, robust, and stable operating system. A handful of characteristics of Unix are at the core of its strength. First, Unix is simple. Whereas some operating systems implement thousands of system calls and have unclear design goals, Unix systems implement only hundreds of system calls and have a straightforward, even basic designs. Okay, hundred system calls are still considered basic here. Second, in Unix, everything is a file. Okay, let's see number two. Oh, number two. Well, okay, not everything, but much is represented as a file. Sockets are a notable exception. Some recent efforts, such as Unix's successor at Bell Labs, Plan 9, implement nearly all aspects of the system as a file. Cool. This simplifies the manipulation of data and devices into a set of core system calls. Open, read, write, lseek, and close. Third, the Unix kernel and related system utilities are written in C, a property that gives Unix its amazing portability to diverse hardware architectures and accessibility to a wide range of developers. Okay, written in C, so it's very easy to get started, I guess, looking at the code. Fourth, Unix has fast process creation time and the unique fork system call. So remember fork, everybody? We learned fork is basically a system call for a process to create a child process that is a copy of itself. Literally a copy, like sharing the same like contents of memory. Yeah. Finally, Unix provides simple yet robust inter-process communication, IPC. So having the ability for two processes or multiple processes to talk to each other and sending messages, data, pretty much. Primitives that, when coupled with the fast creation time of processes, enable the creation of simple programs that do one thing and do it well. So that's the philosophy of Unix. Unix programs should always aim to do one thing and do it well. These single-purpose programs can be strung together to accomplish tasks of increasing complexity. Unix systems thus exhibit clean layering with a strong separation between policy and mechanism. Today, Unix is a modern operating system supporting preemptive multitasking, multi-threading, virtual memory, demand paging, shared libraries with demand loading, and TCP/IP networking. Many Unix variants scale to hundreds of processors, whereas other Unix systems run on small embedded devices. Although Unix is no longer a research project, Unix systems continue to benefit from advances in operating system design while remaining a practical and general-purpose operating system. Unix owes its success to the simplicity and elegance of its design. Its strength today derives from the inaugural decisions that Dennis Ritchie, Ken Thompson, and other early developers made, choices that have endowed Unix with the capability to evolve without compromising itself. Whew. Long intro. Okay. So, Unix was very expensive back then. Let's see. The cost of Unix in the 1980s. This is some motivation here. So how block. Okay. So the cost of Unix in the 1980s varied depending on the version and whether it was for a personal computer or educational institution. Okay, so a Unix license from AT&T was over $100,000, and by 1993 it was close to $200,000. Wow. Okay, so education was anywhere between $5,000 to $7,000. Okay, which is now equivalent to 14 to 20,000 in 2023. Okay, so some background here is that Unix was very expensive for a single license. And this is kind of like the hint of why, or at least the motivation as to why Linux was created. Because Linus needed an operating system that was competent but couldn't afford Unix. So it's like something to keep in mind is that, we always talk about big corporations and their licensing like issues for consumers today. Like this was like a thing too back then, and although we love the design of Unix, some commercial Unix side, whatever, commercial versions weren't very friendly to consumers. So that's I mean this is what I'm getting at. So how I understand it. Anyway, along came Linus. Introduction to Linux. Linus Torvalds developed the first version of Linux in 1991 as an operating system for computers powered by the Intel 80386 microprocessor. So at 386, and for 1991, 386 was a kind of like a weak chip by then. It was like so the 386 came out in 1985. So Intel 386. I'm trying to do this, like take breaks in between so that, we can motivate ourselves, and like just reading a bunch of text is kind of boring too. So it's good to just understand some context. So the 386 came out in October 1985, and Linus was actually still using one in 1991. So it's not like he had the most powerful computer. I think he was just like a college kid too, so he was probably just using whatever he had bought or whatever his parents had bought him for school. So, yeah, this is what he was on. The thing was like only from 12 megahertz to 40. I'm guessing he used like a 33 megahertz version because these things came in like 33 megahertz. But it was a 32-bit chip, so kind of like you can think of it as like the start of like a modern Intel CPU, x86 that is. And pretty much yeah, it was kind of like your typical computer chip for any IBM compatible desktop back in the day. So yeah, people run MS DOS and all that stuff back then on these chips, but this guy wanted to create something else for it. So yeah. Anyway, which was at the time was a new and advanced processor. I don't think so, but anyway, Linus, then a student at the University of Helsinki, was perturbed by the lack of a powerful yet free Unix system. The reigning personal computer OS of the day, Microsoft DOS was useful to Torvalds for little other than playing Prince of Persia. Linus did use Minix, a low-cost Unix created as a teaching aid, but he was discouraged by the inability to easily make and distribute changes to the system's source code because of the Minix license, and by design decisions made by the Minix's author. So Minix was like a different design. There was like a specific, I think it's a microkernel, and we'll figure out what that means later. In response to his predicament, Linus did what any normal college student would do. He decided to write his own operating system. Linus began by writing a simple terminal emulator which he used to connect to larger Unix systems at his school. So he started writing a terminal program first. And that just evolved to Linux. I need to his name is Linus, but we pronounce it Linux. Okay, good. All right. Over the course of the academic career, his terminal emulator evolved and improved. Before long, Linus had an immature but full-fledged Unix on his hands. He posted an early release to the internet in late 1991. So then, I think he had a Usenet. I think Linus Torvalds Linux post. I think it's this one. Here. Okay, so it says, whoa, ads. Okay. Hello, everybody out there using Linux. I'm doing a free operating system, just a hobby. Won't be big and professional like GNU. Won't be big and professional like GNU. For 386 and 486 AT clones, this has been brewing since April. And when was this? I don't know. April and it's starting to get ready. I liked any feedback on things people like or dislike in Minix as my OS resembles it somewhat. Same physical layout of the file system due to practical reasons, among other things. I've currently ported Bash and GCC and things seem to work. This implies that I'll get something practical within a few months and I'd like to know what features most people would want. Any suggestions are welcome, but I won't promise I implement them. P.S. Yes, it's free of any Minix code, and it has a multi-threaded file system. It is not portable, uses 386 task switching, etc. And it probably never will support anything other than AT hard disk, as that's all I have. Oh, how even Linus was very wrong about himself back then. Yeah, here's the entire thread. Here we go. Let's see here. August. So he was working on it for like 4 months by then. Okay. Yeah, late 91. Okay. Use of Linux took off with early Linux distributions quickly gaining many users. More important to its initial success, however, is that Linux quickly attracted many developers, hackers, adding, changing, and improving code. Because of the terms of its license, Linux swiftly evolved into a collaborative project developed by many. Fast forward to the present. Today, Linux is a full-fledged operating system, also running on Alpha, ARM, PowerPC, Spark, x86-64, and many other architectures. It runs on systems as small as a watch to machines as large as room-filling supercomputer clusters. Linux powers the smallest consumer electronics and the largest data centers. Today, commercial interest in Linux is strong. Both new Linux-specific corporations such as Red Hat and existing powerhouses such as IBM, so they're the same company now basically, are providing Linux-based solutions for embedded, mobile, desktop, and server needs. Linux is a Unix-like system, but it is not Unix. So important to remember that. Linux is not Unix. That is, although Linux borrows many ideas from Unix and implements the Unix API as defined by POSIX and a single Unix specification, it is not a direct descendant of the Unix source code like other Unix systems. Where desired, it has deviated from the path taken by other implementations, but it has not forsaken the general design goals of Unix or broken standardized application interfaces. Okay, so it tries its best to be kind of like Unix, but it's not restricted to being Unix because it's not Unix. So yeah, so think of it like they just diverge. One of Linux's most interesting features is that it is not a commercial product. Instead, it is a collaborative project developed over the internet. Although Linus remains the creator of Linux and the maintainer of the kernel, progress continues through a loose-knit group of developers. Anyone can contribute to Linux. The Linux kernel, as with much of the system, is free or open source software. Specifically, the Linux kernel is licensed under the GNU General Public License, GPL version 2.0. Consequently, you are free to download the source code and make any modifications you want, and that's what we're going to do. The only caveat is that if you distribute your changes, you must continue to provide the recipients with the same rights you enjoyed, including the availability of the source code. So if you make changes and you distribute them, you're going to have to also make the code available. Cool. Linux is many things to many people. The basics of a Linux system are a kernel, C library, toolchain, and basic system utilities, such as a login process and shell. A Linux system can also include a modern X Windows system implementation, including a full-featured desktop environment such as GNOME. Thousands of free and commercial applications exist for Linux. In this book, when I say Linux, I typically mean the Linux kernel. Where it is ambiguous, I try to explicitly point out whether I am referring to Linux as a full system or just the kernel proper. Strictly speaking, the term Linux refers only to the kernel. Okay, so when we say Linux, we really think about the kernel, not like a distribution of Linux, which is like Ubuntu, Fedora. Those are distributions. But when we say Linux, we were really talking about the kernel. Okay, so the overview of operating systems and kernels. Because of the ever-growing feature set and ill design of some modern commercial operating systems, Windows, the notion of what precisely defines an operating system is not universal. Many users consider whatever they see on the screen to be the operating system. Technically speaking, and in this book, the operating system is considered the parts of the system responsible for basic use and administration. This includes the kernel and device drivers, bootloader, command shell, or other user interface and basic file and system utilities. It is the stuff that you need, not a web browser or music players. The terms system, in turn, refers to the operating system and all the applications running on top of it. Okay, makes sense. System, stuff that composes, it's made up of all that stuff. Of course, the topic of this book is the kernel, whereas the user interface is the outermost portion of the operating system. The kernel is the innermost. It is the core internals, the software that provides basic services for all other parts of the system, manages hardware, and distributes system resources. So that's the kernel. Stuff that interfaces with your hardware. The kernel is sometimes referred to as the supervisor, core, or internals of the operating system. So the operating system is composed of the kernel and all the other programs necessary to create pretty much a user experience of a computer, right? It makes your computer useful. Typical components of a kernel are interrupt handlers to service interrupt requests, a scheduler to share processor time among multiple processes, a memory management system to manage process address spaces, and system services such as networking and inter-process communication. Okay. On modern systems with protected memory management units, the kernel typically resides in an elevated system state compared to normal user applications. So there's a concept of user space and kernel space. Okay, so divided into two states. This includes a protected memory space and a full access to the hardware. So kernel space allows you to really interface with the hardware. User space is mainly the place where all applications are running, like a state. These are just like states. It gives you certain privileges being in specific states. The system state and memory space is collectively referred to as kernel space. Conversely, user applications execute in user space. They see a subset of the machine's available resources and can perform certain system functions. Directly access hardware, access memory outside of that, allotted to them by the kernel or otherwise misbehave. Okay. When executing kernel code, the system is in kernel space executing in kernel mode. When executing kernel code, so code that is belonging to the kernel, the system is in kernel space. So basically, it's in the state of kernel doing things. Okay. When running a regular process, the system is in user space executing in user mode. So it doesn't have as many features. Restricted for a reason, I guess. Applications running on the system communicate with the kernel via system calls. So for user space applications, you can do stuff with the system directly, or not directly. You can do stuff in the system, but you have to go to the kernel, and the kernel will actually do it on your behalf, you being the user space application. The way to do that is to use an API called system calls. And we had learned that in Head vs. C, where we used a few of them to do some operating system related things. An application typically calls functions in the library. For example, the C library, that in turn rely on the system call interface to instruct the kernel to carry out tasks on the application's behalf. Some library calls provide many features not found in the system call, and thus calling into the kernel is just one step in an otherwise large function. For example, consider the familiar printf function, so getting something to print on the console, pretty much. It provides formatting and buffering of the data. Only one step in its working is invoking the write system call to write the data to the console. Okay. So this is actually the system call that is actually being invoked underneath the hood when you call printf. Conversely, some library calls have a one-to-one relationship with the kernel. For example, the open function library, or the open library function, does little except call the open system call. So we have an open function in the C library that indirectly calls the open system call. So they have the same name. Still, other C library functions such as strcpy should make no direct use of the kernel at all. When an application executes a system call, we say that the kernel is executing on behalf of the application. So when an application uses a system call, it calls a function as a system call, the kernel is going to be executing on behalf of the application. So it tells the kernel to do this specific operation for the application. It's kind of like a kid saying, like having their mom do something for them. So furthermore, the application is said to be executing a system call in kernel space, and the kernel is running in process context. This relationship that applications call into the kernel via the system call interface is the fundamental manner in which applications get work done. The kernel also manages the system hardware. Nearly all architectures, including all systems that Linux supports, provide the concept of interrupts. When hardware wants to communicate with the system, it issues an interrupt that literally interrupts the processor, which in turn interrupts the kernel. So, okay. A number identifies interrupts, and the kernel uses this number to execute a specific interrupt handler to process and respond to the interrupt. So basically, an interrupt is a signal, but then it's not just any signal, it is like a code, right? So an interrupt is a specific code that tells the CPU and kernel to execute a specific function associated with this interrupt code. This specific function is called the interrupt handler. So based off of the specific code of that interrupt, a special function is going to run and respond to that interrupt to handle it. So it's kind of like an event, right? An interrupt is like a very special, high priority event. Your interrupt handler is going to be the event handler, the function that will run in response to that interrupt. So for example, as you type, the keyboard controller issues an interrupt to let the system know that there is new data in the keyboard buffer. Okay. The kernel notes the interrupt number of the incoming interrupt and executes the correct interrupt handler. The interrupt handler, so the function, processes the keyboard data and lets the keyboard controller, so the keyboard controller literally like the little chip inside your keyboard, the hardware, know that it is ready for more data. To provide synchronization, the kernel can disable interrupts, either all interrupts or just one specific interrupt number. See, number, a code. In many operating systems, including Linux, the interrupt handlers do not run in a process context. Instead, they run in a special interrupt context that is not associated with any process. The special context exists solely to let an interrupt handler quickly respond to an interrupt and then exit. These contexts represent the breadth of the kernel's activities. In fact, in Linux, we can generalize that each processor is doing exactly one of three things at any given moment. First, in user space, executing user code in a process, or in kernel space, in the process context. So basically, um, it's actually you're in kernel space because a process requests to be in kernel space through some system call, executing on behalf of a specific process. Okay, so here is user space where all your applications live. Here in this dotted box is the kernel space, and this is the system calls that applications kind of interface with the kernel with. Okay, so any application can invoke some system call, and then actually then the kernel is going to be able to do stuff because of that. Device drivers are just software modules that think of it as little programs that kind of talk to your hardware. Kernel subsystems are just basically like, I guess, like things that the kernel relies on. I can't really describe it, but anyway. So there, just kind of know that there's two worlds, right? There's a user space world and a kernel space world. And kernel space world is where you do all your things related to like directly accessing hardware or like kind of dangerous things that would otherwise like kind of mess up your computer. User space are just your normal applications running on top. Like when we were writing our C programs, we were just creating applications in the user space. So even if we were like doing malloc and like crashing because of seg faults and things like that, we were still in user. We were essentially still in user space in this case. The malloc actually is invoking a system call to telling the kernel to allocate some memory and returning the pointer back. So yeah. And the last thing is in kernel space and in interrupt context. Basically, while it's while it's handling an interrupt, not really associated with any process. So it's handling interrupts. So it could be in kernel space that way too. This list is inclusive, and even corner cases fit into one of these three activities. For example, when your computer is idle, it turns out that the kernel is executing an idle process in the process context in the kernel. So there is like a special process that idles, and that's the idle process. It's considered to be a process. Linux versus classic Unix kernels. Okay. Owing to their common ancestry and same API, modern Unix kernels share various design traits. Okay, with a few exceptions, a Unix kernel is typically a monolithic, static binary, so one program. It compiles into one program. That is, it exists as a single, large, executable image that runs in a single address space. Unix systems typically require a system with a page memory management unit, MMU. So virtual memory, which is all like modern systems at this point. This hardware enables the system to enforce memory protection and provide a unique virtual address space to each process. So it's like the mechanism, like the MMU is the mechanism that allows a program to think that it is the only program executing in the system, thinking that it has all the addresses in RAM available. And how other processes are able to work is that really what the program sees as memory addresses isn't really the real physical RAM addresses. It's kind of like a virtual version of it, and the operating system handles that mapping between the virtual address to the real physical memory. And so that way, whenever a new process needs to run, it basically has its own virtual memory set of memory addresses that map back to another physical address in RAM. So it's that illusion that allows processes to kind of work in this more simplified world where they think that they're the only one in the world and they have all the addresses. So this is the whole point of virtual address space. So Linux historically has required an MMU, but special versions can actually run without one. This is a neat feature enabling Linux to run on a very small MMU-less embedded systems, but otherwise more academic than practical. Even simple embedded systems nowadays tend to have advanced features such as MMUs. In this book, we focus on MMU-based systems. So just assume that every computer that we're going to be working with, or at least in this book, is already MMU capable, meaning that we work in virtual address spaces. Okay, so monolithic kernel versus microkernel designs. We can divide kernels into two main categories of design: the monolithic kernel and the microkernel. A third camp, exokernel, is found primarily in research systems. Okay, well, forget about that. Let's just do the monolithic kernel and the microkernel. Monolithic kernels are the simpler design of the two, and all kernels were designed in this manner until 1980s. Monolithic kernels are implemented entirely as a single process, one process running in a single address space. So basically one big program. Consequently, such kernels typically exist on disk as single static binaries. All kernel services exist and execute in the large kernel address space. Basically, the program gets loaded into RAM and like everything is just in there, like anything it needs. The kernel can invoke functions directly as a user space application might. So it's just kind of like the same programs that we've written in the past. Proponents of this model cite the simplicity and performance of the monolithic approach. Most Unix systems are monolithic in design. Microkernels, on the other hand, are not implemented as a single large process. Instead, the functionality of the kernel is broken down into separate processes, usually called servers. So many programs, microkernels are composed of many small programs, and they'll communicate to each other through like IPC and things like that. So same as like when we had like multiple processes doing IPC with each other through like pipes, files, message passing, things like that. That's how these microkernel programs are working. Um, and each of these programs are called servers. Ideally, only the servers absolutely requiring such capabilities run in a privileged execution mode. The rest of the servers run in user space. So some parts of the kernel of a microkernel get to run in user space. Some will actually run in kernel space. All the servers, though, are separated into different address spaces, so they all run independently. Therefore, direct function invocation as in monolithic kernels is not possible. Instead, microkernels communicate via message passing. So it's kind of like microservices in the cloud, but for operating systems. Okay, so an inter-process communication IPC mechanism is built into the system, and the various servers communicate with and invoke services from each other by sending messages over the IPC mechanism. The separation of the various servers prevents a failure in one server from bringing down another. So if one program in a microkernel crashes, it's not going to crash the system. Versus like if you have a monolithic kernel and it ends up crashing, of course it's going to crash the entire system because it's only one binary. Versus like, for example, if you have a microkernel and like maybe something that's dealing with the file system crashes, at least like there could be a mechanism where if it crashes, it's not going to take down the entire system, but there could be another process that's kind of like maybe like polling for whether or not this file system uh, server, right, this app in the microkernel is up or down. It can kind of just like bring it back up. And some microkernels are like that. They like self-heal in that way. Likewise, the modularity of the system enables one server to be swapped out for another. Because the IPC mechanism involves quite a bit more overhead than a trivial function call, because IPC mechanism involves quite a bit more overhead than a trivial function call, however, and because a context switch from kernel space to user space or vice versa is often involved, message passing includes a latency and throughput hit not seen in monolithic kernels with a simple function invocation. So they are less performant because of the IPC. There's latency involved from sending message from one server to another in the microkernel system. Consequently, all practical microkernel-based systems now place most or all the servers in kernel space to remove the overhead of frequent context switches and potentially enable direct function invocation. The Windows NT kernel, on which Windows XP, Vista, and 7 are based, and the Mach, on which part of the Mac OS 10 is based, are examples of microkernels. Neither Windows NT nor Mac OS 10 run any microkernel servers in user space in their latest iteration. So actually, most modern microkernels now tend to lean towards having all their servers in kernel space, as opposed to having some in user space and some in kernel space now, for the specific reason of performance. It seems like. Okay, so that ends up defeating the primary purposes of microkernel design altogether. All right. Linux is a monolithic kernel. That is, the Linux kernel executes in a single address space entirely in kernel mode. Linux, however, borrows much of the good from microkernels. Linux boasts a modular design and the capability to preempt itself, called kernel preemption. Support for kernel threads and the capability to dynamically load separate binaries, called kernel modules, into the kernel image. Conversely, Linux has none of the performance-sapping features that curse microkernel design. Everything runs in kernel mode with direct function invocation, not message passing, because it is monolithic. It doesn't have these separate servers. Okay, so that's the modus of communication. Nonetheless, Linux is modular, threaded, and the kernel itself is schedulable. Pragmatism wins again. Okay. How much time do we have? Cool. Well, let's see if we can get one more page in. All right. 35 out of 467. Oh, wow. It's not going to be that long of a book then, I guess. As Linus and other kernel developers contribute to the Linux kernel, they decide how to best advance Linux without neglecting its Unix roots. And more important, the Unix API. Consequently, because Linux is not based on any specific Unix variant, Linus and company can pick and choose the best solution to any given problem, or at times, invent new solutions. A handful of notable differences exist between the Linux kernel and the classic Unix systems. Okay, let's see what the difference is. Linux supports the dynamic loading of kernel modules. Okay, although the Linux kernel is monolithic, it can load and unload kernel code on demand. Okay, so dynamic libraries. Linux has symmetrical multiprocessor SMP support. Although most commercial variants of Unix now support SMP, most traditional Unix implementations did not, so multiple cores, multiple CPUs. The Linux kernel is preemptive. Unlike traditional Unix variants, the Linux kernel can preempt a task even as it executes in the kernel. Of the other commercial Unix implementations, Solaris and IRIX have preemptive kernels, but most Unix kernels are not preemptive. Well, that's new to me. Okay. So preemption. Preemption just means that the operating system controls how to switch process, like give another process a turn, because you have many running processes in the system. So preemption is basically the OS decides to switch. And then in non-preemptive systems, it's actually the process that decides that it wants to give another process a turn to execute, because only one thing can execute at a time in a assuming single core, single threaded system. And so back in the day, in older versions like Windows, for example, where there was no preemption, a process can like it can literally lock up your entire system if it decides to not give back some time to the OS to do OS like things, right? And what ends up happening is that then you would have to like just like hard reset your computer, because you would think things are frozen in this case. So bad processes in a cooperative or non-preempted operating system can really cause your system to crash, versus in a preemptive operating system where the operating system is in control of when and how a process executes. If a process were to become unresponsive, no big deal. It's only that process. Another process will just be able to execute because it's going to be switched away out by the OS anyway. So there's that difference there. Anyway, Linux takes an interesting approach to thread support. It does not differentiate between threads and normal processes. So in Linux, there's no such thing as like process, and then like process has many threads. It's just a bunch of threads or thread-like structures. Um, to the kernel, all processes are the same, just some just happen to share resources. Linux provides an object-oriented device model with device classes, hot pluggable events, and user space device file system, SysFS. Linux ignores some common Unix features that the kernel developers consider poorly designed, such as streams or standards that are impossible to cleanly implement. Linux is free in every sense of the word. The feature set Linux implements is the result of the freedom of Linux's open development model. If a feature is without merit or poorly thought out, Linux developers are under no obligation to implement it. To the contrary, Linux has adopted an elitist attitude towards changes. Modifications must solve a specific real-world problem, derive from a clean design, and have solid implementation. So it has to be clean, useful code. Consequently, features of some other modern Unix variants that are more marketing bullet or one-off requests, such as pageable kernel memory, have received no consideration. Despite these differences, however, Linux remains an operating system with a strong Unix heritage. Okay. Linux kernel versions. Linux comes in two flavors, stable and development. Stable kernels are production-level releases suitable for widespread deployment. New stable kernel versions are released typically only to provide bug fixes or new drivers. Development kernels, on the other hand, undergo rapid change where almost anything goes. As developers experiment with new solutions, the kernel code base changes often in drastic ways. Interesting. Linux kernels distinguish between stable and development kernels with a simple naming scheme. So 3 or 4 numbers delineated with a dot represent kernel versions. The first value is the major release, so major release 2. The second is the minor release, 6. And the third is the revision, so 26. So this book was 2.6.34. So major 2, minor 6, revision was 34th revision. Okay. The minor release also determines whether the kernel is a stable or development kernel. I don't think that matters anymore. An even number is stable, whereas an odd number is development. Yeah, this is not the case anymore. I don't think it matters anymore. For example, the kernel version 2631 designates a stable kernel. This kernel has a major version of 2, minor of 6, and a revision of 30, and a stable version of 1. The first two values describe the kernel series, in this case, the 2.6 kernel series. Yeah, so I don't think it matters anymore where it's like odd, even. It's just in general now. It's just regular versions, I believe. Development kernels have a series of phases. Initially, the kernel developers work on new features and chaos ensues. Over time, the kernel matures and eventually a feature freeze is declared. At that point, Linux will not accept new features. Work on existing features, however, can continue. After Linux considers the kernel nearly stabilized, a code freeze is put into effect. When that occurs, only bug fixes are accepted. Shortly thereafter, and hopefully, Linux releases the first version of a new stable series. For example, the development series 1.3 stabilized into 2.0 and 2.5 stabilized into 2.6. Again, don't think that's the case nowadays. Within a given series, Linux releases new kernels regularly with each version earning a new revision. For example, the first version of 2.6 kernel series was 2.6.0. The next was 2.6.1. These revisions contain bug fixes, new drivers, and new features. But the difference between the two revisions, say 2.6.3 and 2.6.4, is minor. And this is how development progressed until 2004 when okay, it explains it now. Okay, great. I thought that this is still written in a way where this is true, but the author is saying, okay, this is all changed now. Okay, so this is how development progressed until 2004, when at the invite-only kernel developers summit, the assembled kernel developers decided to prolong the 2.6 kernel series and postpone the introduction of a 2.7 development series. The rationale was that the 2.6 kernel was well received, stable, and sufficiently mature such that new destabilizing features were unneeded. This course has proven wise, as the ensuing years have shown 2.6 is a mature and capable beast. As of this writing, a 2.7 development series is not on the table and seems unlikely. Instead, the development cycle of each 2.6 revision has grown longer, each release incorporating a mini development series. Andrew Morton, Linus's second in command, has repurposed his 2.6-MM tree, once a testing ground for memory management related things. 2.6 memory management. Okay. Into a general purpose test bed. Destabilizing changes thus flow into the 2.6 mm, so the memory management branch, and when mature, into one of the 2.6 mini development series. Thus, over the last few years, each 2.6 release, for example 2.6.29, has taken several months, boasting significant changes over its predecessor. This development series in miniature has proven rather successful, maintaining high levels of stability while still introducing new features, and appears unlikely to change in the near future. Indeed, the consensus amongst kernel developers is that this new release process will continue indefinitely. And I think that's what they're still doing right now. Okay. To compensate for the reduced frequency of releases, the kernel developers have introduced the aforementioned stable release. This release, the 8 and 2.6.3, 2.8, contains crucial bug fixes, often backported from the under development kernel, for example 2.6.33. In this manner, the previous release continues to receive attention focused on stabilization. Phew, almost there. When you begin developing code for the Linux kernel, you become a part of the global kernel development community. The main forum for this community is the Linux kernel mailing list, LKML. Subscription information is available at this place. Note this is a high traffic list with hundreds of messages a day, and that the other readers, who include all the core kernel developers, including Linus, are not open to dealing with nonsense, so please behave. This list is, however, a priceless aid during development, because this is where you can find testers, okay, receive peer review, and ask questions. Later chapters provide an overview of the kernel development process and a more complete description of participating successfully in the kernel development community. In the meantime, however, lurking on or silently reading the Linux kernel mailing list is a good supplement to this book you can find. Is as good of a supplement. Okay, last one, and then we'll call it a day. I'm getting tired reading. Okay, this book is about the Linux kernel, its goals, the design that fulfills those goals, and the implementation that realizes that design. The approach is practical, taking a middle road between theory and practice when explaining how everything works. My objective is to give you an insider's appreciation and understanding for the design and implementation of the Linux kernel. This approach, coupled with some personal anecdotes and tips on kernel hacking, should ensure that this book gets you off the ground running. Whether you are looking to develop core kernel code, a new device driver, or simply better understand the Linux operating system. While reading this book, you should have access to a Linux system, which we do, and a kernel source. Ideally, by this point, you are a Linux user and have poked and prodded at the source, but require some help making it all come together. Conversely, you might never have used Linux but just want to learn to design a kernel out of curiosity. However, if your desire is to write some code of your own, there's no substitute for the source code. The source code is freely available. Use it! And above all else, have fun. Cool. And we're going to do more source codey things next time around. This is a good intro. Yep, see you next time. Thank you.